Welcome to this explainer. Today we're going to put on our detective hats and decode the hidden language of molecules. We'll be taking raw data and turning it into clear, undeniable chemical realities. We're exploring the fundamental principles of stoichiometry. Now I know that word sounds completely intimidating, but trust me, it's really just the math behind the magic of chemistry.
So let's dive right into this puzzle. How do we actually go from a completely unknown substance to a precise chemical equation? Imagine you're standing in a lab and someone hands you a vial of unidentified white powder. You can't exactly just stick it under a microscope and start counting the atoms, right? Nope. You have to work backward. We have to use mass and weight to uncover its secret identity. It literally is a true detective story.
To crack this case, here is our agenda. 1. Percentage composition unlocked. 2. Finding the empirical formula. 3. The true molecular formula. 4. Calculating chemical equations. And 5. Summary and the real world.
Section 1. Percentage composition unlocked.
Okay, so before we can even begin to figure out what a whole molecule looks like, we kind of need to know who's in the room, right? We have to look at the total weight and figure out what fraction belongs to each element. It's exactly like slicing up a pie. You just take the weight of one specific element inside a single molecule, divide that by the total weight of the entire molecule, and then multiply by 100. Boom! That gives you the percentage by weight for that specific element.
Let's see what that looks like in practice with calcium phosphate. Out of its entire molecular weight, which is 310, exactly 20% of that is pure phosphorus. And we find that simply by taking the weight of the phosphorus atoms, which happens to be 62, and dividing it by that total 310. Just like that, it gives us a really concrete ratio to start working with.
And this isn't just theoretical, it has huge real-world applications. For instance, agricultural scientists use this exact math to calculate that a 5-kilogram bag of urea fertilizer will deliver exactly 2,333.3 grams of crucial nitrogen directly to the soil. They are absolutely not guessing here. Because they know the total molecular weight of urea is 60, and they know the nitrogen inside it accounts for 28 of that 60, they can say with certainty that exactly 46.6% of whatever urea they pour on a field is pure nitrogen. This is literally the math that helps farmers feed the world with absolute precision.
Section 2. Finding the empirical formula.
Think of the empirical formula kind of like a basic architectural blueprint. It won't tell you the final size of the finished building, it just gives you the absolute simplest ratio of the materials used. It's the most reduced, bare-bones representation of a compound possible. So say your compound is made of carbon and hydrogen, the empirical formula just tells you the foundational ratio. Like, okay, we have 1 carbon for every 2 hydrogens.
Now, to find this blueprint without getting completely overwhelmed by dense data, we just follow 3 really logical steps to distill our percentages down to atomic ratios. First up, we take those percentages we literally just figured out. Second, we divide them by the element's unique atomic weight. This is crucial because it levels the playing field, so we're comparing atoms to atoms, not just arbitrary weights. And finally, we divide all those answers by the smallest number in the bunch to create a nice, clean, whole number ratio.
So, applying that exact methodology here, a compound with roughly 29% sodium, 40% sulfur, and 30% oxygen reduces down perfectly to the simplest empirical ratio of Na2S2O3. Notice how in step 2, the relative atoms for sodium and sulfur both came out to 1.266. By dividing everything by that 1.266, we got a ratio of 1 to 1 to 1.5. But, well, we can't exactly have half of an oxygen atom in real life, right? So we just double the whole shebang to get our final whole numbers, 2 sodium, 2 sulfur, and 3 oxygen.
Section 3. The true molecular formula.
All right, so while the empirical formula gave us the basic proportions, the molecular formula gives us the actual real-world reality of the molecule. This is essentially the ultimate goal of all our chemical detective work. This formula tells us exactly how many individual atoms of each element are physically bonded together in a single, actual molecule floating around in our beaker.
You can really see the difference here. The basic blueprint of glucose is just CH2O, but the actual sugar molecule that is coursing through your veins right now, that's scaled up 6 times to C6H12O6. That foundational ratio of 1 to 2 to 1 is perfectly maintained, but the physical molecule itself is literally 6 times larger than its simplest empirical form.
So, how do we scale up our blueprint to find that true identity? We just find the ratio between the total molecular weight and our basic empirical weight. That gives us our magic multiplier, which we call N. Honestly, it's incredibly straightforward.
If your actual molecule weighs twice as much as your blueprint says it should, then your multiplier n is just 2. You just multiply every atom in your blueprint by 2, and boom, you've uncovered the true molecular formula.
Let's walk through this specific example. Here, we see how an empirical weight of 45 and a molecular weight of 90 gives us a multiplier of 2, which transforms CHO2 into our true molecule, C2H2O4. It shows us that the empirical weight of CHO2 adds up perfectly to 45, but the data tells us the actual molecular weight is 90. Well, 90 divided by 45 is 2. We multiply our base CHO2 by 2, and just like that, the mystery is completely solved.
Section 4. Calculating chemical equations.
Now here is where things get really wild. When these molecules interact, they completely rearrange their identities to form entirely new products. The elements themselves don't disappear, right? They just change partners. But when they do change partners, their fundamental properties transform completely. It's literally how toxic, highly explosive gases can combine to form the refreshing water we drink every day.
A perfectly balanced chemical equation is so much more than just a random string of letters on a page. It's a comprehensive ledger, telling us the exact proportions, the exact masses, and even the gaseous volumes involved in a reaction. It's the ultimate recipe. If you know how to read it, you can predict exactly how much of a product you're going to get from a specific amount of raw material, literally down to the gram.
So let's see how all this builds into our final procedural flow. This is what gives us the power to calculate exactly how much product will yield from any reaction. Step 1, the equation has to be perfectly balanced, the exact same number of atoms on the left as on the right. Step 2, we calculate the weights under those balanced formulas. From there, step 3 is just simple mass ratios. Oh, and step 4, if we're dealing with gases at standard temperature and pressure, we use a magic number. 1 mole of any gas always occupies 22.4 liters.
Okay, looking at the complete electrolysis of water here, we can prove step by step that 18 grams of H2O will liberate exactly 16 grams, or 11.2 liters, of oxygen gas. How? Well, the balanced equation shows us that 36 grams of water yields 32 grams of oxygen. Therefore, logically, if we cut the water in half to 18 grams, it cuts the oxygen yield in half to 16 grams. And since 32 grams of oxygen is 1 full mole taking up 22.4 liters, our 16 grams is exactly half a mole, taking up 11.2 liters. The math is just so incredibly elegant, and it is consistently perfect every single time.
Section 5. Summary and the real world.
So these 3 pillars form the absolute foundation of all chemical stoichiometry. They act as the ultimate translator between raw, messy laboratory data and true chemical understanding. You start with the weight percentages, you reduce them down to a base empirical ratio, and then you scale them up to find the true molecular identity. This is the unshakable bedrock of chemical analysis.
And the really cool part is that these concepts scale up beautifully into even larger universal laws. They allow chemists to predict gas volumes and mole behaviors on massive industrial scales. Whether you're using Lusak's law to measure reacting volumes of gases, or you're applying Avogadro's number to calculate literal billions of precise molecular interactions, it all fundamentally relies on the precise stoichiometric ratios that we've just decoded together.
So now that you officially have the tools of a chemical detective, I want to leave you with this thought. How much of our physical world can you decode simply by knowing the numbers? Next time you look at a fertilizer label at the store, or watch a fire burn, or honestly, even take a breath, remember that behind all of it is an elegant, highly predictable mathematical equation just waiting to be balanced. Thanks so much for joining me on this explainer. Keep asking questions and keep decoding the world around you.